Ever feel like the universe is playing this giant game of hide and seek? Like it's got this whole elegant set of rules, right? This master plan. But we only get these like cryptic clues. Well, physicist A. Garrett Lisi
Yeah.
might just have found a new clue in that cosmic game, and you guessed it.
Okay.
Today's deep dive, all about his attempt to crack the code using something called
Using the E8 Lie group.
the E8 Lie group. There we go.
Yeah. And what I think is so fascinating about Lisi's work is that he doesn't just throw up his hands at the complexity of physics.
Right.
He starts with a problem I think we can all relate to, which is just the sheer mess of it all.
Talk about a cosmic case of too many tabs open. We've got the standard model of particle physics explaining all the small stuff. General relativity handling the large-scale structure of the universe, and they agree about as well as, like, cats and cucumbers.
Exactly. And Lisi is saying, what if the problem isn't that the universe is messy, but that we're looking at it the wrong way? Like, he thinks there might be this hidden elegance,
Okay.
this underlying structure that ties everything together.
And this is where E8 comes in, right?
This is it.
I'll admit, when I first saw E8 Lie group
Yeah.
in your notes, I thought we were about to decode, like, some ancient alien script or something.
It doesn't sound that different.
Right.
But instead of aliens, think of E8 as this incredibly intricate, multidimensional shape, a sort of cosmic blueprint. Lisi's proposing that if we could map out all the forces and particles in the universe onto this shape, onto its points, onto its symmetries, it would reveal a deeper level of order.
It's like that aha moment when you finally find the right organizer for your entire life and suddenly everything just makes sense.
Yes.
But in this case, the organizer is this crazy mathematical shape, and the life it's organizing is the entire universe.
Yeah, that's a great analogy. And to understand how revolutionary this idea is, we need to sort of get a handle on the before picture, which is the current state of particle physics,
Okay.
which, as you mentioned, can feel a bit jumbled.
Okay, so let's talk about this before picture, the standard model. Can you give us the crash course version without setting us into a physics-induced coma?
I'll try. The standard model is essentially the best theory we have for explaining the fundamental building blocks of matter and the forces that govern them.
Okay.
It's given us incredible insights into things like electromagnetism,
Right.
the strong force that holds atoms together, and even the weak force that's responsible for radioactive decay.
So it's like the periodic table, but instead of elements, it's the even tinier particles that make up those elements.
You got it. But here's the catch. While the standard model is incredibly successful at explaining a lot of what we observe,
Yeah.
it's also a bit like trying to fit a square peg into a round hole when it comes to gravity.
Ah, gravity, that old chestnut, always messing things up.
Always.
So the standard model explains all these forces, all these particles, except for the one force we're most familiar with in our everyday lives.
It's the elephant in the room, or maybe the black hole in the particle accelerator.
Right.
And this is a big part of what Lisi is trying to solve. He's saying, okay, maybe the standard model isn't broken, but it's incomplete.
Okay.
What if we just need to find the right frame to put it in, the frame that includes gravity naturally?
And that frame is E8.
That's the idea.
So instead of starting a new physics model from scratch, he's looking for a deeper level where all the pieces, even gravity, just click into place.
That's the gist of it. And one of the ways he does this is by taking existing pieces of the standard model, pieces we know and love,
Right.
and shows how they might fit within the geometry of E8.
Okay, now we're getting to the good stuff. Give us an example. How does he actually connect a real-world force to this, like, abstract E8 shape?
Let's take gluons, for instance. These are the particles that are responsible for the strong force.
Okay.
The force that binds quarks together to form protons and neutrons.
So gluons are like the super glue of the subatomic world.
You could say that.
Yeah.
Now, Lisi connects gluons to a smaller, simpler shape called G2, which itself fits neatly within E8.
Okay.
It's like, discovering a secret compartment within that E8 organizer that's perfectly sized for those gluons.
So it's not just randomly shoving gluons into E8 and hoping for the best. There's a mathematical reason, a geometric logic to where everything fits.
Exactly. And he does something similar with gravity and the weak force.
Okay.
Those two forces that the standard model has trouble reconciling.
Right.
He suggests they could be two sides of the same coin.
Wait.
Two aspects of a single, more fundamental force.
Gravity and the weak force being two sides of the same coin. That's kind of mind-blowing when you think about how different those forces seem to us.
It is. And just like with the gluons, Lisi finds a geometric representation for this relationship within E8 using a shape called F4.
Okay.
So imagine, gravity and the weak force, these two seemingly different things, as two sides of the same coin. Lisi suggests that E8 might be the hand that's flipping that coin.
Whoa.
This is what he calls gravi-weak unification.
Okay.
And it's a pretty big deal, if true.
Okay, I'm starting to see why E8 gets physicists so excited.
Yeah.
It's like finding this hidden Rosetta Stone that translates between all these different forces and particles. But how does he go from fitting individual pieces to unifying everything? This is where I assume things get really interesting.
You're catching on quickly. And you're right, this is where Lisi takes a giant leap forward.
Okay.
He shows that when you combine the mathematics of those two shapes, F4 representing gravity-weak unification and G2 representing the strong force, they fit perfectly within the larger structure of E8.
It's like those Russian nesting dolls, but instead of dolls, it's fundamental forces fitting inside ever larger, more encompassing mathematical concepts.
That's a great way to put it.
Thank you.
And this perfect fit, this elegant nesting of shapes within E8, this is at the heart of Lisi's theory.
Okay.
It suggests that all these seemingly disparate forces and particles might just be different facets of a single underlying reality governed by the geometry of E8.
So we've got this beautiful complex shape in E8. We've got connections to existing particles and forces.
Right.
But where do the actual particles themselves fit into this whole E8 picture?
That's the million-dollar question.
Right.
And it leads us to one of the most, I think, mind-blowing aspects of Lisi's theory,
Okay.
and another one of E8's remarkable properties. Triality.
Triality. Okay, that sounds ominous.
Yeah.
Or at least like it requires a physics degree to understand. Don't worry, I'm pretty sure we can talk about triality without like breaking the universe or our brains.
I hope so.
But maybe you should take the lead on this one.
Okay. Let's imagine E8, this intricate ship that we've been discussing, as having a kind of hidden symmetry. Imagine taking a perfectly symmetrical snowflake
Okay.
and rotating it 60 degrees.
Mm-hmm.
It looks the same, right?
Right.
That's rotational symmetry.
Yeah, I get that. Snowflakes, those overachievers of the symmetry world.
Well, E8 has something even wilder. Imagine rotating that snowflake, but instead of just in a circle, you're rotating it through higher dimensions.
Okay.
And you find not one, not two, BUT, 3 ways to rotate it that all give you the exact same shape back.
Whoa.
That's triality.
Okay.
3 seemingly different views that are all just aspects of the same underlying structure.
Okay, my brain just did a somersault, but I think I'm following. E8 has this hidden trifold nature where 3 rotations lead back to the same starting point.
You got it. Now, here's where Lisi makes a connection that'll really fry your circuits.
Okay.
He proposes that this triality, this 3-sided nature of E8, might be the reason why we have 3 generations of particles in the standard model.
Wait a minute. You're saying those 3 generations, electrons, muons, tau particles, and all their quark counterparts could just be different rotations of the same underlying E8 point?
That's exactly what he's suggesting.
That those seemingly distinct particles are just different perspectives on the same fundamental thing.
It's a mind-boggling idea, and it beautifully illustrates the kind of deep hidden connections he's trying to uncover with E8. It's like those optical illusions where you see either a vase or 2 faces.
Right.
But it's really just one image with 2 interpretations.
Okay, that is officially the coolest thing I've heard all week. But even if this triality thing explains the why of 3 generations, it doesn't really tell us anything about how those generations actually differ from each other, right? Like, why is a muon so much heavier than an electron if they're both just different views of the same E8 point?
You're hitting on one of the biggest remaining mysteries, even within Lisi's framework. While he offers some tantalizing hints about how particle masses might arise from E8, it's one of the areas where the theory is still under construction.
Okay.
It's like having the blueprint for a skyscraper,
Right.
but not quite understanding how they're going to get the plumbing to work on every floor.
So, a work in progress?
Yeah.
But with some seriously high-stakes plumbing involved. And speaking of things still under construction, I noticed the paper also mentions a whole bunch of new particles and fields predicted by E8. What's the deal with those? Are we talking about a whole new cast of, subatomic characters?
You could say that. Unifying theories in physics often come with the exciting and slightly terrifying prediction of new undiscovered particles.
Yeah.
It's like realizing that our map of the universe might have some significant blank spots.
Blank spots that could potentially rewrite everything we thought we knew?
Exactly.
So, what are some of the, standout new kids on the block that E8 suggests might be out there?
Well, there's this new quantum property he introduces called the W quantum number.
The W quantum number.
Which is about as catchy as a physics term can get.
Maybe not quite ready for prime time, that name.
Right.
But what does this W quantum number actually do? How does it change the game?
Think of it as adding a new rule to that cosmic game of hide and seek we were talking about earlier.
Okay.
It's like discovering a hidden mechanic in the universe.
Right.
A new way that particles can interact or behave that we'd never even considered before.
Okay, so it's not just a new particle, but a whole new property that particles can have, something that influences their behavior.
Yeah.
That's a pretty big deal.
It is. And some of these particles with the W property, like those found in what Lisi calls the X-phi field.
Okay, the X-phi field.
Yeah. They could be the key to solving another one of those big physics head scratchers we were talking about.
Yeah.
The mystery of why particles have the masses that they do.
Okay. Now things are getting really interesting. We're talking about potentially explaining one of the biggest unknowns in physics.
We are.
You've got my full attention.
Imagine for a moment that we had been trying to weigh subatomic particles for centuries.
Okay.
But we were missing a crucial piece of information, this W property. It's like trying to bake a cake, but you don't know how much flour to use.
And Lisi's saying, hey, I think I found your missing measuring cup. It's this W quantum number, and it's hiding over here in this E8-shaped cupboard.
You're getting it.
I'm trying.
These new particles, with their W properties and their interactions within this X-phi field, might just be the missing piece of the puzzle that lets us finally understand why a top quark is so much heavier than an electron, for example.
It's like those detective shows where they finally find the one clue that makes all the other evidence fall into place.
Yes.
But in this case, the crime scene is the entire universe. So these new particles with their W properties, are they just theoretical constructs? Or is there a chance we could actually detect them?
That's the beauty of a good scientific theory. It makes testable predictions.
Right.
And Lisi's theory is no different.
So we're not just talking about elegant math here,
Right.
but potentially observable,
Yes.
testable predictions.
That's right.
That's what moves it from the realm of cool theory to, whoa, this might actually be how the universe works territory.
Precisely. And one of the most exciting possibilities is that these new particles Lisi predicts could be spotted in experiments like those at the Large Hadron Collider,
Right?
the LHC.
Okay.
Imagine the headlines, E8 particles found.
Right.
Physics about to get a whole lot more interesting.
Talk about a cosmic plot twist. Okay, so let's say, just for fun,
Okay.
that we do start finding evidence for these W particles.
Okay.
This XV field.
Yeah.
What changes?
Yeah.
Paint me the physics after E8 picture.
Well, for starters, it would mean rewriting textbooks,
Right.
which is always a good time.
Always fun.
But more importantly, it would be a paradigm shift in how we understand the universe at the most fundamental level.
Okay.
It would be confirmation that this search for a unified theory, a
Wow.
theory of everything,
Right.
wasn't just a physicist's pipe
It
dream.
would be like finding the missing instruction manual for the universe.
Yes.
The one that explains how all the pieces fit together.
Exactly.
But wouldn't it also open up whole new areas of research? Like,
yeah.
if we understand the universe's, like, fundamental code,
Yeah.
couldn't we potentially, like, use that knowledge?
The possibilities are pretty much endless at that point.
Right.
Imagine, harnessing the power of these fundamental forces in ways we haven't even dreamed of.
Yeah.
New energy sources, materials with unheard of properties, computation that makes our current computers look like abacuses.
It's like we're living in a sci-fi novel
I know.
where cracking the code of physics unlocks a whole new level of technological advancement.
Exactly.
Okay, I have to ask, warp drive. Are we getting warp drive out of this?
Let's not get ahead of ourselves.
Okay.
But in all seriousness,
Yeah.
while warp drive is still firmly in the realm of science fiction,
Okay.
a deeper understanding of the universe's fundamental forces could lead to breakthroughs we can barely even imagine right now.
My brain is already on overdrive imagining the possibilities.
Right.
But even if Lisi's theory doesn't pan out exactly as he's described it,
Right.
this whole deep dive has been incredible.
It's really cool stuff.
It really makes you look at the universe differently,
Yeah.
to see those hidden connections between things.
And that's the mark of any truly groundbreaking theory, isn't it?
Right.
It shifts our perspective,
Yeah.
even if it doesn't have all the answers. It reminds us that there's always more to learn, more to discover, and the universe is full of surprises just waiting to be uncovered.
Speaking of surprises,
Right.
before we wrap up,
Yeah.
are there any, like, big lingering mysteries that even E8 doesn't quite explain?
Oh, absolutely. One of the biggest ones is that link between E8's triality and the 3 generations of particles.
Oh.
While Lisi's theory suggests this beautiful connection,
Right.
the exact mechanism for how it works is still unclear.
Okay.
It's like we found the bridge between 2 islands,
Right.
but we haven't figured out how to build a road across it yet.
So we might need to delve even deeper into the mysteries of those W quantum numbers, that
Yeah.
XV field, to truly understand how those particle generations arise.
Exactly.